right here in this window, they don't look the same. What I want to do right here is evaluate a limit, and we're going to see what happens with this limit, and we can use it to kind of explain why the function on top in the numerator looks a lot like the function on the bottom when x gets big. So first of all, if I try direct substitution, what am I going to get? If I try direct substitution here, this first term here is going to be what? Infinity minus infinity plus 3 over infinity. A lot of unknown stuff there. A lot of infinities. I don't know what infinity minus infinity plus infinity is. I can make a guess. I do know that this infinity is bigger than this one because it's raised to the fourth power instead of just to the second power. But I still don't know. So I need to make this look different. What could I do to make this look different? Lewis? Yeah. Just divide all the top terms by that bottom term, that x to the fourth. So this is equivalent to the limit as x approaches infinity of, what's x to the fourth divided by x to the fourth? 1 minus 39x squared divided by x to the fourth? 39 over x squared plus 70 divided by x to the fourth? And plus 3 over x to the fourth. That one's easy. Everybody see where these came from? Now, this is pretty simple. We can use direct substitution now. Why? What's going to happen with this term? Yeah, it's going to go to 0 because the denominator is going to go to infinity. So this is going to be 0. This is going to be 0. This is going to be 0. And so this is equal to 1. Now, I have the top the top polynomial divided by the bottom polynomial. When x gets really big, it gets really close to 1. What does that mean? What does it mean if I take something and divide by something else and I get 1? It's the same thing, right? When we take anything and divide it by itself, we get 1. What this is saying is, if I take this big function here and divide it by x to the fourth, when x gets really big, it's just 1. Which is saying that when x gets really big, they're essentially the same thing. So let's look at the graph again. Here's the graph of x to the fourth minus 39x squared plus 70x plus 3 compared to the graph of x to the fourth. And I'm going to zoom out. And I'm actually not going to zoom out that far. And look at what they look like now. Now, I said I didn't zoom out that far. I'm at, what is that, 2.5 million up at the top. That's pretty far on the y-axis. But look at the x-axis. Is the scale on the x-axis really that ridiculous? No. By the time we get to negative 40 and 40 on the x-axis, these functions look nearly identical. So the end behavior of that blue function and the red function are the same. So we can use, for big numbers, we can use the red function to describe the blue one. And the red one is much simpler. Does that make sense? Okay. So I want you guys to guess right now, knowing what you just saw in that one, what would the end behavior, what simple function would the end behavior be described by for each one of these? Let's start with this one. Oh, I heard a lot of people say x squared, and I heard Alyssa say, what'd you say? Did you say something? Oh, y equals x squared? I actually disagree. And here's why. We want the ratio, the limit of the ratios of the functions to equal 1, right? And if I divide by x squared, what's the first term going to be? 5x squared divided by x squared. Now, I probably don't have to go much further, and you can tell me what's going to happen here. We're going to have 5 minus 4 over x plus 1 over x squared. And what's this ratio going to approach? 5. So that means that 5x squared, when x gets big, is 5 times as big as x squared. So what do you think it is now? Good. So this is going to be very closely approximated, especially for large values of x, by this 5x squared. So if you zoomed out far enough, you would not be able to distinguish 5x squared minus 4x plus 1 from just 5x squared. All right, how about the next one? You guys are smart. How about 4x squared minus 1? Cool. Okay, how about the bottom one? Perfect. So what we want to look at here is which part of the numerator and which part of the denominator are kind of dominate those respective areas. So this is going to be approximated by 5x to the fifth over 2x to the fourth, which can be simplified to what? 5x over 2. So this rational function here, a polynomial divided by a polynomial, you can approximate that or predict its end behavior based on the leading terms on the numerator and the denominator, and you would divide both of those. Does that make sense? So if you would zoom out on that function, it would actually look a lot like a line with a slope of 2.5 when you get out far enough. Kind of cool, huh? All right, now, because of that, we can do these types of limits very quickly using some kind of quick tricks. So when we say that the function has end behavior similar to another function, what we're saying is it's getting really, really close to that function. So let me go back real quick, just one slide here. So that means that if I took the limit of this function, this whole thing, as x approaches infinity, what would it go to? It would go to 5x over 2, and what happens when x goes to infinity? It goes to infinity. So this function looks a lot like this function, and the limit of this one as x goes to infinity is infinity. So what do you think the limit of this one as x goes to infinity is? Infinity. It's going to be the same. So if we can figure out what the end behavior function is, then when we take the limit as x approaches infinity, it's really easy. We can just use that simpler function rather than the big one, the more complicated one. Now, all the ones that we did there, those are all going to go off to infinity. Here's some examples where they won't. So this first one here, any suggestions on how to approach that using what we just talked about? First of all, if we try direct substitution, we're going to get infinity divided by infinity. That's no good. So what function would closely approximate that? Would have the same end behavior as that? Good. So you guys said 1 over 2x, which is just the simplification of this. So you take the leading term in the top and the bottom, and the limit as x approaches infinity is going to approach the same as it would for the end behavior function. So that's the same as the limit as x approaches infinity of 1 over 2x, which is... Plug in infinity there for x. What do you get? 0. Does that make sense? Okay. How about this other one? So this is going to be equal to the limit as x approaches infinity of 1/2. So 3x cubed over 6x cubed. The x cubes cancel, so it's a limit as x approaches infinity of 1/2. Plug in infinity there. You can't really plug it in anywhere, can you? So you just get 1/2. So this function is going to approach 1/2 as x approaches infinity. What does that mean? 1/2 is what for that function? It's an asymptote. It's a horizontal asymptote, right? Now we could do the same thing as x approaches negative infinity with all of these and get the horizontal asymptote going to the left. All right? So, quick tricks here. If we want to find the limit as x approaches infinity for any rational function, a polynomial divided by a polynomial, I'm going to go back a slide real quick. Right there. Anytime the numerator is bigger than the denominator, the power in the numerator is bigger than the power in the denominator, we're going to have an end behavior function with an x still in it in the numerator, and so that limit's going to go where? To infinity. So if the power in the top is bigger than the power in the bottom, it's going to go to infinity. If the power in the top is less than the power in the bottom, then we're going to have x's left in the denominator, and the limit's going to go to 0. If the powers are the same, then what are we going to do? What's the trick there? Divide the leading coefficients. Exactly. So in this case, the limit as x approaches infinity of 3x squared with all this stuff over 6x, I'm sorry, I said squared, 3x cubed over 6x cubed. You just divide the leading coefficients, you get 1/2. Does that make sense? All right. More. If we plug in, this is kind of a conceptual limit here. If we try direct substitution, when we plug infinity into x here, what's the sign of infinity? It doesn't really exist, does it? But we do know something about it. What do we know about it? It has to be where?
In between 1 and 1.
In between -1 and 1, exactly. So it doesn't matter how big the number is. When I use direct substitution with infinity for x here, I'm going to get some number between -1 and 1 on top. Okay, so it's not a constant. It's oscillating, and it's going to oscillate forever. But I do know the value has to be somewhere between -1 and 1. If I put x in, or I'm sorry, infinity in for x here, what do I get? 0. No. Well, okay, we get infinity on the bottom, which means what? We're taking some number between -1 and 1 divided by infinity, and we're going to get, you guys said it, 0. Okay? So this is a little bit different than what we talked about yesterday. It's not a constant divided by infinity, but it's a bounded number divided by infinity. So it's a number that can't get any bigger or any smaller than a certain value, so we know that is going to approach infinity. I'm sorry, we know it's going to approach 0. How about this one? We're going to have 5 times infinity minus something between -1 and 1. So it's going to be pretty much dominated by this, divided by infinity. What's going to happen here? Any ideas?
Can we do the end behavior thing?
Okay, we could do the end behavior thing. We have to be a little bit careful about it because we want to make sure that with the trig function in there, the end behavior still acts the way the polynomial would. To make sure about that, we could do what Lewis has been suggesting and do what? Split it up, yeah. So let's look at the limit as x approaches infinity of 5x divided by x is 5 minus sine of x divided by x. One of the properties of infinity, one of the properties of limits that's really useful, and it may seem obvious, but we do need to mention it. The limit of a difference is the difference of the limits. So this is the same thing as saying the limit as x approaches infinity of 5 minus the limit as x approaches infinity of the sine of x over x. Okay, those mean the same thing. So what is the limit as x approaches infinity of 5? Okay, this part here is 5. What is this part right here? We just did that one, right? 0. So it's going to be 5 minus 0, which is 5. You would never really be expected to split it up like this. You don't have to rewrite it in separate limits, but you can evaluate each part of a limit separately and then combine it as suggested by the operations. Okay, any questions about those? I was kind of hinting at this earlier. This is something you may want to write down. This can be very useful. So the limit as x approaches infinity of f of x is the same as the limit as x approaches positive 0, or 0 from the right, of f of 1 over x. And the reason is 1 divided by infinity is positive 0, or approaches 0 from the right. What it means is, in any infinite limit, we can change it to a limit approaching 0, which can be a lot easier to work with at times, just by replacing x with 1 over x. So let's do that for this particular example here. Rather than saying the limit as x approaches infinity of x times the sine of 1 over x, how could we rewrite that? That's the same as the limit as x approaches 0 from the right. What if it was a negative infinity? Then we would approach 0 from the left, exactly. So limit as x approaches 0 from the right of, I want to replace x's with 1 over x. So we replace that x with 1 over x. The sine of 1 over x is going to become sine of x. And what limit do we have now? What limit is this? We just did it. It's the sine of x over x, right? Which is 0. Now, I'm not saying we couldn't have done this one the other way, but what happens here in this one, if we leave it like this, we plug infinity in for x here, what do we get? Infinity, right? And we plug infinity in here, we get the sine of 0, which is 0. Does anybody know what infinity times 0 is? We don't know. It's indeterminate. It could be infinity. It could be a constant, it could be 0. So this is a situation where we had to manipulate it in order to get a little more information out of it. Okay, only a few more. This looks kind of complicated. It's really not. I want to sketch a graph here that has all of these properties. Looks like a lot, doesn't it? So, as x approaches negative infinity, f of x approaches 3. What does that mean? What? So as x approaches negative infinity, as we go off to the left, the function is approaching 3. What does that mean about that 3? We're going to have a horizontal asymptote at 3. And same thing going to the right. So to the right and to the left, we're going to have a horizontal asymptote at 3. So I'm going to put 3 on the axis here, and I'm just going to draw in a horizontal asymptote. I'll fill in more with the picture if I get it later. Excuse the sloppiness of my drawing, but it's kind of hard to write on here sometimes. Okay, as we approach 1 from the left, the function approaches infinity. What do you think that means about, I'm sorry, negative 1. What do you think that means about the value of the function there, or what the function looks like? So as we approach some constant value on the x-axis, the y-axis is approaching infinity.
Is it a vertical asymptote?
We're going to have a vertical asymptote, exactly. So at negative 1, we're going to have a vertical asymptote. And we know which way it's going from the left. Which way is it going from the left? Is it going up or down? It's going up because it's going to positive infinity. So we're going that way. And I could probably go ahead and continue the graph here. We're going to get something that looks like that to the left of negative 1. To the right of negative 1, it's also going to be up, right? So we're going to have the function going this way to the right of -1 also. Okay, as x approaches 0, then the function approaches 0. What does that mean? I'll give you a hint. It's going to go through that point. Or if it doesn't go through that point, it's going to look like it goes through that point and there's going to be a hole there. So I should probably redraw this here. We're going to have something like that. Okay? We good with that so far? As we approach 3 from the left, we go to -infinity. What does that mean? Going to be a vertical asymptote at 3. So I'm going to draw this. And we're probably going to get something, I don't know what it's going to look like, but it's going to look like that. And as we approach 3 from the right, it's going to be, is it going to be up or down? It's going to be up here, so it's going to be going up as we approach from the right. And remember, we have that horizontal asymptote at 3, so it's going to look like that. Yes?
How come you're allowed to go to that horizontal asymptote?
The horizontal asymptote only describes what happens as x gets really big. A function can actually cross a horizontal asymptote and then approach it as x either goes to infinity or -infinity. Yes?
So that'd be an asymptote to the constants you get after you second, like in the first two.
What's that? So, right here, you could have different values. Is that what you're asking? So you could have different horizontal asymptotes going to the right and to the left. Okay, that is everything you need to know from section 2.2. We kind of covered it by doing examples. If you're having trouble with the type of problem, you may want to look in the book, and then I will spend some time answering questions tomorrow. I'm going to try to cover all of the material from 2.3 tomorrow, and then give you time to work on Friday, pretty much the entire hour. That's my goal.